Hey, howdy everyone. We are still in this machine learning course in the state of prerequisites, establishing some fundamental concepts that will support us as we move forward in a variety of machine learning methodologies. So let's carry on. We've got just a couple more things to cover, but we're getting there. We're getting there. So let's talk about multivariate analysis. This will be a very cursory treatment of the topic, really just to provide some fundamental concepts that we'll need later on. Why do we care about multivariate workflows? Well, it turns out that our modeling efforts in the subsurface tend to be multivariate. And in fact, they're getting even more multivariate than they used to be. We're doing more with modeling the entire Earth, not just some subsurface objective, but the overburden above it. Really, a lot of that has to do with trying to close a variety of loops. For instance, if you want to build a model and then run some type of forward seismic calculation on it, get a forward seismic model, and then you can check to see if the synthetic seismic matches the real seismic that was acquired, that would be closing a loop. Closing loops with regard to production to make sure you match production information of flow rates and so forth. There's lots of loops that we can close. Unconventional reservoirs make things even more multivariate. It brings in all kinds of rock properties we may not have considered. Vitrinite reflectance as a measure of maturity, total organic carbon. We may also be concerned with other types of indicators that help us map and try to understand, unravel the mystery that is unconventionals. And so we're working with a lot more variables all the time. It's getting even more complicated when it comes to the multivariate setting. Now, why do we want to cover multivariate methods? Well, we want to cover some general multivariate concepts that are really going to be prerequisite for everything that we're going to be doing furthermore in the discussion around machine learning. Many of our machine learning methodologies are working with multiple predictor features, inputs to the model to make predictions of potentially multiple outputs or response features. And so we want to be able to account for that. We need to understand the relationships. We're going to be talking about multicollinearity and so forth. And so we need to just at least have a very brief discussion about multivariate. We can talk about visualization through scatter plots. We can talk about quantification through different measures of correlation. And we might just decide to work directly with conditional probabilities, work directly with conditional statistics in order to understand multivariate problems. So let's go ahead and get into some multivariate analysis. Now, a very basic first step would be to perform the calculation of a scatter plot. There's nothing magical about this. You could imagine trying to understand the relationship between porosity and permeability for this sandstone formation and just plotting up the data relative to porosity for each measure plotted against the permeability of each measure. Now you could imagine if you were to take this data set and just plot the histogram of porosity and the histogram of permeability, you would lose a lot of information. You would not see these features, these striations or lines that occur only when you scatter plot and look at the bivariate relationship, the relationship between the two variables or features at the same time. So we would lose a lot of information. There's a natural grouping here that probably relates to grain size or to some type of facies or maybe mineralogy and so forth. Another thing is that we may fail to recognize certain structures or features in the model that can impact our ability to use the data within a machine learning methodology or may encourage us to do some type of transformation forth and so forth. So if we look at this situation right here, we have an example where porosity versus acoustic impedance, and the relationship you could argue is a very basic linear bivariate relationship. Then in expectation, the porosity is related to acoustic impedance by a function like this. Now, there's quite a bit of cloud around it, and if you look at the cloud, the degree of scatter, if we look across different ranges or bins of acoustic impedance, that range of scatter is somewhat constant. The variance does not vary over the range. The variance of porosity does not vary over the range of acoustic impedance. That would be what we call homoscedastic. Now, if we have a situation like this, porosity versus permeability, as often is the case, as we increase porosity, if we look at the variance is very low for permeability given low porosity, but look at the variance for permeability given high porosity. This is a case that is clearly heteroscedastic. Okay, so we can look at the shapes of the relationships, the general tendency towards nonlinear type of relationships and expectation, and the variance varying, which would be heteroscedasticity versus something that's linear and has homoscedastic. This is all important and will furthermore constrain the way that we work with our data. It may encourage us to do a transformation before we start working with our data. We could, of course, have categorical variables that when we plot them up, we find there's only a set number of possible categories that occur. Facies 0, 1. It would be one example of that. And then we might have continuous variables like acoustic impedance, which will have a range with respect to each one of those facies types. We may have constraint relationships. Here we have a case where we have high degree of scatter for low permeability values for acoustic impedance, and when you get to high permeability values, it narrows. There's some type of physical constraint that we don't have extremely high or low acoustic impedance in the high permeability measures. How do we quantify a relationship between two variables? The simplest way to do this is to use the Pearson's product moment correlation coefficient. Everybody just calls this the correlation coefficient. This is the standard correlation coefficient. It provides a measure of the linear relationship between two variables. In fact, if you look at the equation, it really is just a standardized covariance. And the covariance would be if we removed the standard deviations of each one of the variables x and y. And if we were just to divide by the number of samples, it becomes an average product of the difference between each one of the samples and its mean multiplied by each other. Now this is very interesting, and so I've drawn that down here. This is simply the covariance shown down here, and the covariance is related to the correlation coefficient by this relationship here, where we just take and standardize by the standard deviation of each one of the features, the two features we're comparing to each other. And what we'll realize then is that it's a measure of how two features vary together. You would imagine this result would be maximal if you have consistently high values of y paired with high values of x. In other words, the samples have a feature y and x which are high together. That would result in a high product. And if we systematically have low values, they would be large negative values because they would be very low relative to the mean. They'd be big negative values. The product of them would be a large positive, and so we get a maximum correlation coefficient when we see samples that are high together in both features and also low together in both features. Now, of course, we can see that the covariance and the variance are related to each other, as I just mentioned. That if you look at the equations for a covariance and you compare it to the sample variance right here, the only difference is we took the sample variance, expanded the squared term, and then we replaced one of them with the other feature, y instead of x. So we're in fact seeing with a covariance how two features are varying together. Pretty cool stuff. The Spearman rank correlation coefficient, or known most of the time as rank correlation coefficient, provides a measure of the degree of monotonic relationship. It's not as sensitive to the linear relationship, which is really good. That's quite useful. It relaxes that. And it actually does a nice job of dealing with outliers. What does it do? All we do for the Spearman is we simply replace all of the values, the sample for x and y, and the means x and y, and the standard deviations x and y with the rank transformed data samples, mean, and standard deviation. What's a rank transform? Super easy. Take the x feature, sort it in ascending order from lowest to highest. And then what you do is you simply say the lowest value of all, that very low value, gets a rank of 1. It's the lowest value. The highest value gets a rank of n, where n is the number of samples. And so if I had 100 data, the value with the highest value for porosity, or whatever x might be, would receive a rank transform of 100. And the lowest value would receive a rank transform of 1. Now, if you do that, that does a nice job of accounting for nonlinear types of features and also outliers within the data set. Let's take look at an example right here of the correlation coefficient being calculated from data sets. So we have data sets X and Y, scatter plot, correlation coefficient 0.96. No surprises here. Not much scatter, nice linear relationship. That's a high correlation coefficient. Should have mentioned the correlation coefficients range between -1 and 1, 1 being perfectly positively correlated, increasing together, and -1 being perfectly negatively correlated, decreasing together. Now, if we have nonlinear features like this is half of a parabola, we still get about a 0.96. It does okay with some slight nonlinearity within the data set, but you can see it's already starting to penalize it. If we have a negative relationship, we get negative correlation. Now, here's where the wheels really fall off the wagon. If you had a random distribution of data and you put one outlier way out here, really far outside the range of the others, it comes back with a correlation coefficient of 0.95. One outlier is greatly inflated the correlation coefficient. And if you plot the relationship of a parabola from the negative to the positive, the symmetric parabola, look at what happens in the correlation coefficient. If we'd filled in more data over here, it would actually drop probably pretty close down to 0. So let's just make a basic comment around correlation, since we're doing a lot of discussion about correlation right now. This is a very famous example right here. I think this was taken directly from Wikipedia. Correlation does not imply causation. You require a true experiment where we control for all and only change one of the variables or features in order to assess or attempt to assess causation. But we're very careful about assessing causation. Correlation does not equal causation. Why? Let me show you an example. Number of churches, a number of crimes. Okay, so can we say that churches cause crime? What's going on here? Well, in this famous example, what's going on is that we have not controlled for population. Large cities have more churches, have more crimes. What's the underlying implicit variable or confounding variable that we've forgotten to, or we neglected to include? Population. Population causes churches, population causes crimes. If you in fact calculated the correlation for a large city of churches versus crime, you'd find out that there's almost no, or probably no, correlation whatsoever. So this is a famous example. In fact, if you're ever interested, there is an entire website called Spurious Correlations. Spurious Correlations does a very nice job of mining through large databases and looking for really funny correlation coefficients. And so, for instance, they found, here's the relationship over year on year for 2000 to 2009, divorce rate in Maine, and the margin consumed. And so what can we say? Can we say margin causes divorce? Or maybe divorce causes margin? I'm not sure. Spiders killing people, the frequency of spiders killing people, can be related directly to, with a pretty high correlation, to about a 0.80 of the length of the words in a national spelling bee. Okay, so you can see there's all kinds of opportunities here to see this. Now let's go and let's take an example data set. We'll just do this in Excel really quickly. I cut and pasted it here. I have the example spreadsheet available to you. Generate a random set of numbers. Make them span between values of 0 and 1, or 0 and 2, or -2. Just make a random set of values. If you calculate the correlation coefficient, you can do that. And then what you do is you add one extreme outlier. If you were to perform that exercise, when I did it, I got 0.18 for a random set of data. If I had a larger data set, it'd probably be close. It would converge on 0, but it's not a large data set, so I could have a positive or negative correlation from random. And then I'll put one outlier in. It's not that extreme. I get 0.66. Okay. Now what would happen if we do the rank correlation coefficient? What's the difference? You see our original data back here? If I employ the rank transform, then what will happen is each value is replaced with the integer rank within the data set in X and Y. Look at that. So this value right here, I think there's 50, 52 data here or something like that. The highest value in porosity permeability is that orange outlier. It now gets the top rank. But look, all these other data now span uniformly along that rank transform. It removes the effect of the outlier. And it helps us, if we have some nonlinear behaviors, it will help potentially linearize the problem for us a bit. Okay, so if you calculate now the correlation coefficient without the outlier, still very close to what we had before for the regular Pyrcz product moment correlation coefficient, 0.18. But with the outlier, it only increases it to about 0.24. It's less sensitive to the outlier. Now, I mentioned before, if you have a parabola, which is just simply the y is equal to x squared relationship shown right here, we could calculate the correlation coefficient between -1 and 1, and we'll find out the correlation coefficient, in fact, is 0, which is fascinating because if the correlation coefficient is telling you about the degree of relationship between x and y, this is a perfect relationship. It's shaped very nonlinear, but it is a very good predictive relationship. If I know x, given this data set, I perfectly know y. But I'm getting a correlation coefficient of 0 because it's sensitive to nonlinear features. Now, if you calculate the correlation coefficient just between the range of x between 0 and 1, it jumps up to 0.96 because this is nonlinear, but it's not that nonlinear. It departs a little bit, and so you do okay. The rank correlation coefficient comes back as a correlation coefficient of 1.0 because it's able to account for the nonlinear feature. It's more robust with nonlinear features. Now, there's a type of correlation you don't hear about very much that I think is very cool when it comes to multivariate analysis. It's called partial correlation. Now, if I'm calculating the correlation coefficient between x and y, what do I do with the problem like I had with the churches and crime, where I have other features I'm not accounting for, like population? Well, the idea here is what we do is we can, in fact, control for x and y, control for all of the other features while accounting for the relationship or quantifying the relationship between x and y. Okay, so how do we do it? Well, it's quite straightforward. We take x and we perform a linear least squares regression to predict x from all of the other features. Okay, so we're trying to find the relationship between x and y, controlling for all the other features. We had m features in total, so it means we'll have m minus 2 z features, which are just the bucket for all the other features that we're not using right now, not the ones that we're trying to get the correlation between. Okay, so we take them and we form a multi-linear regression model of all these features to predict x. We repeat the same thing for y. We predict y given all of the other features, z1 through m minus 2, which are the features that are not x or y. So we now have a relationship or a model that allows us to predict x and y from all of the features that we want to control for, we want to remove from the equation. So how do we do that? We take and calculate the residual. We predict x at every single one of our training data locations or data value locations using our model. That's our x star. That's the prediction of x. We then calculate a residual, which is simply subtracting the true x from the model x, And then we can plot that. And if we plot that, we now have the residual versus all of the other features. Now, I should clarify, I've shown this for simplicity as a single axis, but you can imagine it's going to be a multi-dimensional axis, right? It's going to be m minus 2 axes all being represented here. We do the same thing for y. We take the prediction of y from our multilinear model given all of the z1 through m minus 2 features, and we get a residual. Now you notice this is a residual now, so it's going to probably be, you hope, if it's unbiased, centered on 0, and you will have negative and positive values for the residual. Now what do you do next? All you have to do is calculate the correlation coefficient between the residual in y and the residual in x. This is a partial correlation coefficient. We have actually controlled for the relationship controlled for all of the other features that were not included with x and y, for all the z 1 through m minus 2. Now, there's a range of different assumptions that get made with this methodology. The assumptions include the fact that we're only counting for linear relationships. That makes sense. And you are assuming that there's bivariate Gaussian relationships between each one of the variables. That if you were to produce a matrix scatter plot, as we will right away, that they would all look like Gaussian ellipsoids with linear relationships, homoscedastic, as I already mentioned. Now, if you're interested in trying out partial correlation for yourself, I have built a simple Excel spreadsheet with a data set which demonstrates the calculation by hand of the partial correlation coefficient. I think this is great. If you want to learn the method, go ahead, use the spreadsheet. The most complicated thing it does, multilinear regression. So actually not at all complicated at all. But you'll see the calculation of we got the original plot of the x versus the other property, and we just use one z feature for simplicity, and we got the residual, and we do the correlation coefficient between each of them. Now, I mentioned matrix scatter plots. We may find that we have many features to work with, and we want to try to understand the relationships. You could use in Python or R, you have really nice graphical packages. This is an example from Seaborn package within Python. One line of code and you get a very nice matrix scatter plot. What you have is facies, porosity, permeability, acoustic impedance. Facies is a categorical 1 or 0, 0 or 1, and you've got them plotted against each other. Facies, porosity, permeability, acoustic impedance, facies, porosity, permeability, acoustic impedance. So this is the facies versus facies. Doesn't make sense to look at that scatter plot because it'd just be 2 points on top of themselves. Or actually, sorry, it would actually be 4 points at the corners. Wouldn't be very interesting. So instead, what we do is we just show the histogram on those diagonals. And within Seaborn, you can decide how you want to display. And then we have the cross plots between porosity and facies, permeability and facies. You see how facies is categorical, so there's nothing in between 0 and 1. You can also look at porosity versus permeability, or permeability versus porosity, and you'll see that these are the mirror image of each other. So, super powerful way to explore the relationships, the bivariate relationships, which means just 2 features at a time relationships between your entire data set. Now, at the same time, I do recommend looking at conditional statistics. I've talked about correlation coefficients, the Pearson product moment correlation coefficient, the rank Spearman correlation coefficient, partial correlation coefficients. They all rely on some assumption of the general relationship, linear or something kind of close to linear, or what I should say is monotonic in the case of rank. The cool thing about conditional statistics is what you can do is you can take a data set with acoustic impedance, porosity, plot it up, and then bin it. You see these red lines? These are bins. And within each bin, you can calculate the conditional distribution. Now, for brevity and for clarity, I've just plotted the expectation or the average within each bin, and the P10, the 10th percentile, and the 90th percentile. You can plot that out and you can look at the general relationship. Now, while this data set is somewhat nonlinear and kind of complicated, it has higher variability here and the higher values and so forth. When you look at the conditional statistics, now you can actually see a very clean relationship, the general change in expectation going from high to low, the general increase in variability and the high values. You can just see that very nicely. So I do recommend at times when you have enough data to support it, just go ahead and directly calculate conditional statistics to understand multivariate relationships. It's pretty powerful stuff. Now I have a nice example, well-documented workflow in Python. It's available on my GitHub account. Here's the link for it right here, the short link. If you go to my Python numerical demos repository, you'll find it as one of the subsurface data analytics workflows, and it's multivariate is the name of the workflow. All right. Now, so what have we covered here? That's kind of basic takeaways that you could use. Well, in the presence of multivariate relationships, We must jointly model the variables. We must account for their relationships with each other. We may have to deal with high dimensional relationships, and we'll talk more about feature selection, dimensionality reduction pretty shortly. We'll be doing that right away. Limitations of correlation. It's a degree of linear correlation, does not imply causation. Anytime you're working with correlation, even if we're working with rank, which is monotonic, don't assume causation from it. We need a controlled experiment, carefully controlled experiment, in order to try to get to causation. And we would like to have some type of physical, plausibility explanation, so forth behind it. But we can visualize and use rank correlation coefficients and so forth. We can use conditional statistics to try to understand a very data-driven approach. Just no model at all. Just look at the data, look at the conditional statistics, and try to understand what's going on in the multivariate sense. All right, and you also did see a matrix scatter plot, which was one line of Python code to get that entire plot. Very powerful stuff. And so that's a cool opportunity too, to use just Python code to get really nice, powerful visualizations very easily. All right, I hope you found this lecture useful for you. We are getting through some prerequisites to get ready for machine learning in this course. I am Professor Michael Pyrcz. I am a professor at the University of Texas at Austin. I work in geostatistics, data analytics, and machine learning, and I'm always happy to discuss. You can find me on GitHub, Twitter. I'm also on YouTube, of course, with these lectures. I'm the Geostats guy. All right, everybody take care. Okay, bye.